Thank you, everyone. So this is a long day, I know. So this will be the last session. I'm Suvendu Mohanty. I'm from Amazon. I am a senior machine learning engineer and a voice AI specialist, especially. I work on the Amazon devices for a while, almost like 4 years. I'll talk about a little bit like the topic, which is you can relate or everyone can relate in the daily life. What is the technology behind it, and how we can solve it on the LLM perspective. Voice AI is the, I can say the core of our life at this moment, right? Each devices that you see, being it Amazon Alex, I can say it is in every household, or your phone, or how you connect to the, or you interact to the voice LLM application. So the tech behind it, we need to understand like how it has improved, or if you wants to build a voice based application, what's the system architecture or the component that you should aware about it. Before I start, I'll give you a funny thing that I always start with, right? I was like driving to catch my board my flight, and I don't want to name the airline, and I was stuck at the traffic. And when I realized I'm going to miss my flight, I called to the customer care of that airline, and that from the opposite, a nice voice came. It is IVR system that started prompting me about what is your issue. I started telling, okay, this is my issue. I'm going to miss my flight. Can you please suggest me it is only 45 minutes, right? That voice agent start talking to me like a normal in a flat tone, right? It didn't understand my context, my urgency, my voice, the way I wanted to speak to a human, right? So technically that's where the lag is at this moment, right? That's where your business fails. Your customer get disappointed where your voice AI or your tech don't understand the context, didn't able to understand the people's emotion, what exactly they want, and how the your voice AI should react. So there are lots of architecture. My presentation is little different, I can say. If you're not able to see, let me know. I can zoom in a little bit so that it will be more visible. So not so a voice AI system, if you are familiar with it, I'll simplify a little bit. A voice AI system, when you speak to any voice like device, right? So that's your user input. And when you talk as a speech, your speech will be converted as a audio, I can say that simplifying audio packet, right? And that audio packet is sent back to the server that is called your STT, speech to text, right? So your will be converted into a text. And we have the different component on the speech to text module. I'll go over it. But think about whatever you speak, it will be converted into a text. And that text goes back internally to a LLM reasoning engine. I'm considering the LLM because that's the tech world right now. Earlier it was not, but I'll not go back to that. But consider your text will be go back to your LLM. The way you are writing on a ChatGPT prompt, you can think about when you speak, it goes back to as a prompt and send back to the ChatGPT. I'm considered like Llama or Queen 2.5 VLLM LLM simplify the LLM model, and your text goes back to there, and it understands your context, your historical thing, then you understand your user perspective, then sends a text back. And there is another component, is called your text to speech. That means it converts back whatever the response that you get from your LLM to a speech. And finally, your the speech that has been converted from your text to speech, that means your TTS, your TTS, that goes back to your audio output. That means your device output, right? So this is a very much simplified way that how your architecture looks like in a nutshell, right? Internally, how your system works. but there are lots of internal component to it, right? I'll highlight one of the core problem of it, right? If anyone have ever interacted with a voice AI system 2 years back or 1 year back, right? You must have noticed your voice AI was not that fluent that you see today, because earlier what used to happen is your voice AI was not that much intelligent enough to understand the context of a user what it is speaking. Right now, if you speak to a voice AI, let for example ChatGPT or anything that you speak, so the time that you speak, you'll get the immediately the response. That's a massive engineering behind it. The engineering is called basically the end-to-end latency. That's where you feel there is no lag. Let if your a standard human interaction latency is 700 milliseconds. If you'll see your end-to-end latency, that means when you speak and you get a response, it's more than 700 milliseconds, then you will not feel the real-timeness, then you feel the lag. So the entire architecture I will talk about considering the latency as well, how we are minimizing the latency. Right now, you can think of is human latency is 700 milliseconds, but using the we are able to achieve 350 milliseconds latency end to end. That's a massive improvement, and we're trying to make it more, right? Let's move forward. There are lots of things to talk about. I'll go over a little bit on the technical, one of the technical component that sometime back I was talking about early days when you will be interacting with a voice system, you must have heard some lag, or you must have felt some lag that your voice will be responding little later, right? Not immediately. And you know why? That is a component is called VAD. That is your voice activity detection. That means early days, what you used to do is we have a VAD system which basically tells, okay, let for example, I'm telling something. Okay, can you give the flight status? Right? When I'm telling like, can you give a flight status, all are one token. So until I complete a sentence, your VAD will wait. And once I complete it, then it sends back to the server. That means your LLM to get a response, or my database to get a response. But that is actually not going to very effective. In the current scenario, in the current tech world, how we work is it is called your semantic endpointing. What is the semantic endpointing is? Instead of we are relying on your VAD system, semantic endpointing is there is a system which can understand your semantics of your statement. Even though have not completed it, it will be taking the partial statement and send that back to the server, and it will be in a streaming fashion rather than on a batch fashion. That makes the system more realistic and more real time, and makes more end-to-end latency improved. So I'll talk more about that. Many people have talked about the LLM already. So I'll not go over the LLM again. I'll talk more about the LLM in the context of the voice, right? So what it is called as LALM. This is a new term you must have heard, or if you know it, then pretty good. So it is called a large language model, but for the audio. Large audio language model. That is a audio version of it. For example, let's think about I'm talking hello, and I'm talking hello, how are you? Wow, and I'm talking wow. So each of the statement, when I'm talking to the wow or wow, so both the words has a different meaning, right? So for example, think about it. If I'm telling like, wow in normal way, if I'm astonishing way, if I'm telling like wow, then my LLM doesn't understand. It understands only the wow, right? How it will be understand like the phonetics of it, or the way I speak, or my vocab, or my feeling. It doesn't understand. And it gives you response as a flat. Whether you will be telling like, okay, can you give me the flight status? Or what is the flight status? That doesn't matters for LLM if it doesn't understand the context of it, feelings of it, a person, right? That's the where the lag is. That's where the standard LLM is. Your standard LLM doesn't understand like your people's feeling. So it takes your voice, flats out into a text, send that text back to the your LLM. LLM gives the response back. And your LLM doesn't understand the people's emotion. But your LALM, has been featured or it has been trained or fine-tuned for audio engineering. That means it has the feature to understand the people emotion. It understands the context of the way the word has been spoken or has been spelled, right? And person's way they speak is different and it will like match to the rhythm or the way they wants to hear. That's the trick behind of it. And how does it? We call as LLM tuning. So that's what the main focus is, right? So I'll go to the LLM fine tuning sometime back. So before that, I just want to say that before going to the LLM fine tuning, I'll hop over to this system architecture once more, and I will tell you why I told, because in the system architecture, this is the LLM component. Before going to the LLM component, there is a big component already there, which is called your STT, right? So if I will be improving my LLM alone, that doesn't make any sense here. I need to make sure that my data that is, or the voice that is going to the LLM, that need to be pre-worked, or it should be pre-worked with the way your voice LLM expecting. So what are the changes that is required or the architectural change that we have done on the speech to text, STT, basically? I'll talk about that, then I will go to the LLM fine-tuning part. So a standard STT in a nutshell is a pretty much standard. The STT is not a new technology. It's been evolved, or like I can say 15 years back, and it has evolved a lot. But for a context of a understanding the human's emotion, so the STT has been tokenized, has been configured into the different layer. I'll simplify this. Think about, you are talking a same like raw audio voice. Once it comes to the raw audio voice in a 16 giga format, it comes. So each of our person's voice, two major component present. One is emotion, and one is in terms of how I speak, what is my pitch, what is my phonetic, right? And the emotion is something like whether I'm in hurry, whether I'm happy, whether I'm like angry, what sort of emotion. It is on my voice, right? A human can understand. But how I can make sure that my LLM understand this? It's not very easy. So we have introduced like, there is another component, it's called audio encoder. So what this audio encoder does is, so it has two adapters. First is the semantic adapter, and another is the acoustic cue former. I can basically tell you like the semantics adapter is, if I will define a simple term, semantic adapter is the text or the speech that you speak, and the text that is associated with it is called semantic adapter. And the acoustic adapter is all the acoustic feature of the voice is called acoustic adapter. And part of this, so that was missing basically. So when we send a audio, we two adapters, separate adapter, and both adapters, and their job is to differentiate between your voice and the acoustic out of it. And once that voice and acoustic has been created, then they are been tokenized. And those, we have two tokenizer for this. For your semantic adapter, we have a semantic tokens, and we have for the acoustic adapter, we have acoustic tokens. And for both the things, we have a different models created and has been trained. Both are the neural network engines, and both the neural network engines has been trained to deal with those kind of waveforms or the media data. And once those two has been created, and both this, I can say semantic tokens is like what has been said, and acoustic is how has been said. If you get both of them, then you create a context window connecting both the things, like both the semantics and the acoustic. So earlier we used to pass only the acoustic. We are not, sorry, semantic. We are not able to pass the acoustic. Now it both has been passed together along with to the context window to the LLM. Now LLM doesn't only get the text. It also get a context of your acoustic features of the text. Once we send it LLM, then we will talk about how the LLM basically has been trained to work on your acoustic feature. For example, I will tell you now. You will go to the ChatGPT, and if you will pass acoustic feature along with your text, it doesn't understand, right? Because it is a simple LLM. It is a text-based LLM. It is not capable of understanding your acoustic feature of your voice. So you need to train it, and how it has been trained, how the LLM has been trained. So let's go to that. I hope it is visible to everyone. So LLM fine-tuning is, I can simplify this. Let's think about, I'm taking a text-based LLM has been trained. My chart like OpenAI or anyone like Llama model, which is a standard LLM, is a text-based LLM, which has already been trained, and it is given to me. And I want to use that part of like my voice app API. And if I'll tell that just I will use it, you will not get that response. You will get the flat response as a normal you will be getting like 2 years back. So what are the changes that we have done? So we have done the 3-stage training process. That I can say that fine-tuning process, not training process, fine-tuning process. What this fine-tuning 3-stage tells? First is the stage 1, where the cross-model alignment. What is this cross-model alignment is telling? You have taken a Llama model. It is a 1 billion parameter. What we do is we freeze the 1 billion parameter. We don't touch it. We freeze the Llama model 1 billion parameter. We don't touch any of the parameter change. And also, we have an encoder, audio encoder. That means the previous audio encoder we have used, those two audio encoder that we have used on the STT phase, that also we freeze it. And we apply the LoRa technique. The LoRa technique, it is a standard procedure that has been applied for your any LLM fine-tuning as well. You can use the same LoRa technique here. So you can use the 8-bit, 16-bit, or whatever the best on your resources. You choose it. And what you do is you apply you get a bunch of audio text, which is basically distorted and which is basically taken on a condition which is very critical to understand for a LLM. And you extract out those text and you feed that and you start training on top of it. That's the first phase of it. That is using the LoRa technique. And what we use the part of the LoRa technique is the result that we are expecting out of this LoRa technique. I'll just tell that it is just to understand what is the acoustic feature looks like apart from the text feature, right? On the first phase, that's what we do. And once your first phase is done, and once like in my model understand the acoustic feature of it, but still it is not capable enough to produce the realistic acoustic feature. And the second phase is called your soft level emotion SFT. So it is a very much SFT technique. So why we have created a SFT technique? Think about, I trained my LLM and I given the acoustic feature, but still my LLM is not smart enough to understand the emotions. If you're not familiar with the SFT, it is called supervised fine-tuning. What is the supervised fine-tuning? Supervised fine-tuning is basically, you can think of a human intervention is required there. And where a human will be leveling based on diversity of the parameter. For example, I'm a human and I'm training like SFT data. I'm leveling the SFT data. I'm hearing like a audio voice. Let, for example, hey, what is your flight status? I'm going to miss my flight. Can you please tell me? And I will be, okay, can you tell me my flight status? It is on Friday. So these two statements are different. When a audio enabler or audio encoder, a human encoder, when he will hear it, what he will do it will take the two statement and he will attach a technically a label to it. That means each of the statement to statement, it will attach a stated numeric number to it along with the text. And that is basically done through the SFT method. And urgency, your neutral, frustrated, those kind of article statement they will take and it will attach the numeric. So why we are doing it? So that my LLM would understand more context and deeper context of the human emotions on top of understanding, just not to understand just the encoder, voice encoder, rather than understand the emotions as well. And once this stage 2 is done, the SFT is done, then we go to the third stage is called reinforcement learning. Think about SFT is done, and it is a standard procedure in the industry that after the SFT, we go to the reinforcement learning, right? So RLHF is the standard reinforcement learning that we go for, and it is same. So here the reinforcement learning is a little different. So what we do is we build the algorithm that I have taken GRPO. You can take any of the algorithm. There is a latest algorithms are available. Every month we have 2 to 5 algorithms are created on the industry. So you can take any of the algorithms and just do the reinforcement learning on top of it. What is this reinforcement learning is doing? So what you will be doing is you create a teacher model, and your teacher model will be creating the same voice. You take 2 voice samples. You send, after the SFT phase, you send the voice sample to this model. It generates a output of it. And you take a teacher model, you pass that, and you pass both the things. Then you pass that into the responses to the reinforcement learning. Then there you create a feedback loop, feedback to this model, and based on the responses, it will be learned from this. And this is very essential. If you will not do it, then what will happen is understand the emotions, but the way it creates the emotion text, it will not be perfect. It will be normalized. Always it will try to normalize if you will not do this. In the acceptive phase, it will be do the normalization. So that's why it is very much essential to do this reinforcement learning. So after this third step is done, then my LLM model is ready for processing the voice data. And it understands the human emotions. But here the context, like the pipeline doesn't end. I'll switch back a little bit further, go back to the system architecture again, and I'll just want to highlight the third component of it. Very much important. Third component is called your text to speech. Very interesting. 1 year back, to be precise, 1 year back, when you will be talking voice AI system, you must be heard a robotic voice. And nowadays, if you talk to you must be getting an automated call. When you pick up the call, someone talking behind your phone, and you cannot detect whether it is an actual human or a robot. How it is possible now? What is the tech behind it? This is the tech behind it. This is the component. This is not the LLM. This is the tech component which enables that richness or expressiveness or humanishness in your voice. This is the component. It is your text. Your LLM is very much capable of creating the business sensible information. It understands your context. It creates the workflow. But how it goes back to the user in a voice AI system, that's how it interact to the user in a humanish way or expressive way. That's what your text to speech is. Let's look into the little bit of text to speech, how the text to speech improvement works basically. Early days, when it is a text to speech is nothing, it is a diffusion model, standard diffusion model. Anyone aware about it? It is a standard diffusion model. It is nothing new. It has been in the market for almost 10 plus years. So the take what the improvement that has been done, along with the LLM sends us a response, but along with the LLM response that has been sent, which has been, the LLM has been like fine-tuned for, sorry, I'll do a time check. I have 5 minutes only. I'll fast track it. Along with the LLM that is sending the response, which LLM is been fine-tuned, how my text to speech has been improved and how it will understand. Think about, it is a very important component I will tell. Here you can see that it is called AVD, right? So it is basically an valence. And the visual valence is basically what I can say, is a voice component, I can say. Is a voice component, is a voice engineering component of how we speak or how we spell it, right? So this is a matrix. And what happens, like for example, you are writing to a OpenAI, show me something, you are writing a text, and it is giving a text response. But in the voice AI system, it is not only give a text response. Along with the text response, it gives a AVD matrix as well. It is a matrix. And this matrix composed, right, that tells what are the emotions of the human. What exactly, how the SST should take this emotion. And the SST module, what it does is, it takes the text output along with the AVD, and what it does is, it converts into the 3 part. The first part is your basically semantics. Semantics is basically normal text. And your timbre is nothing, is your speaker's identity. That means your speech, what is your voice pitch, how you speak. And I've not included here how it understands the timbre, but there is a concept is called voice cloning. The way you speak it, your AI can talk it. And this is nothing, the magic is behind the timbre. So you take a sample of it, and I do the SFT, and I done sampling through the RHFL method. I have trained my model to generate a voice sample like you. And where the VAD will be having your voice speech. And that is nothing in your timbre. And second is the AVD vector. AVD is nothing like, as I mentioned, RHFL, valence, and the dominance. These are the 3 major part of a voice thing. Okay. Then these 3 been passed to my basically diffusion model. I can say that diffusion model, but this is not a standard diffusion model. Sure. Okay, I'll wrap up. So it is basically the diffusion standard. It will go to the diffusion model. The diffusion is it is a flow matching CPF model, which is very optimized. And it goes back to the vCoder, which is basically a standard vCoder, which converts like your diffusion model response to the expressive audio. So this is the entire architecture. With the short limitation of time, I'm not able to cover everything, but I'm happy to take any questions you have.
So we have time for one question because we are going to be kicked out 1:30. So one quick.
Yeah, I was curious about how it works on different genders and cultures and languages. Is it accurate for those, or is it more accurate for specific, like standardized voice that we usually have? It's the same way images tend to be standardized for the biases we have in our culture, the white male for doctor and nurses are female, that kind of thing.
Yeah, you're correct. So now it is not generalized. It is all about the training process, how you have trained your LLM. And your LLM, if you have a diversity of your audio data, sample data, both male, female, or diversity of the language or different age groups, right? It understands. If you are more diversity, and your model will be more diverse, and it will create the VAD score, more accurate VAD score. And based on the VAD score, the response will generate.